Hi students, welcome to my YouTube channel. Today we are going to discuss the second problem, which is based on truss. Okay, so in this problem, for the 2-bar truss shown in figure, determine the nodal displacement, stresses in each element and reaction at the support. Take E, that is Young's modulus, 2 into 10 raised to 5 Newton per mm square, and area is 200 mm square. Okay, here in this problem, okay, this is the structure. Here we have two elements. This is element 1, this is element 2. Here it is fixed and here it is fixed, and here one downward force is acting at node 2. Here we have total 3 nodes, node 1, node 2, node 3. Okay, so first I will construct the same structure in a line diagram. Okay, if you construct that the same line diagram, it will be like this is element 2, here this is node 2, and this is element 1. Okay, here at this point this is node 1, node 2, and this is node 3. Okay, so at this node 1 we will be having Q1 as well as F1. So in vertical direction Q2, F2. Here at node 2 in horizontal direction Q3, F3, Q4, F4. Similarly at node 3 in horizontal direction this is Q5, F5, here Q6, F6. At each node you will be having one x direction displacement and one y direction displacement. So we have 3 nodes, Q1, Q2, Q3, Q4, Q5, Q6. Okay, this is element 1, this is element 2. Here we have the vertical distance as 300 mm, and from this point to this point, as per the diagram we have 500 mm, and from here to node 1 that is 400 mm. Now the length of second element is 500 mm. Okay, that is parallel. Okay, so if we extend this line, this will be 500. Okay, what about this element 1? Here the vertical distance is 300 mm and horizontal distance is 400 mm. With the help of Pythagoras, we'll calculate the length of element 1. Okay, length of element 1, that is 1 is equal, that is length 1 is equal to under root here 400 square plus 300 square. 400 square will be 16,000 plus 300 square will be 9,000. Okay, so after adding we'll get 25,000. So after solving we'll get length as 500 mm. Okay, so here this length is 500. So here I will write L1 is equal to 500 mm and L2 is equal to 500 mm. Okay, now we'll construct nodal coordinate data. Okay, next step is we have to create nodal coordinate data. As here we have 3 nodes. First is node number, that is 1, 2, 3. Okay, then x and y. Okay, if you consider node 1, okay, if it is origin, check the distance. This distance 500 plus 400, that is 900. Okay, here this is the reference point. Now here we don't have any vertical distance, that because these 2 points are on the same axis, so y is 0. Now if you consider node 2, here the horizontal distance is 500 and the vertical distance is 300. For node 3, horizontal distance is 0 because these two are on the same axis, so it is 0. Okay, now the vertical distance is 300. This completes nodal coordinate data. Okay, this is for node 1, Here for node 1, the horizontal distance is 900 and vertical distance, these 2 points are on the same axis, so it is 0. Okay, for node 2, the vertical distance is 300 and the horizontal distance is 500. From this reference, the horizontal distance is 500. For this node 3, vertical distance is 300 and that horizontal distance is 0 because these 2 points are on the same vertical axis. Okay, next we have to create element connectivity data. We'll construct element connectivity data. Next is element connectivity data. First is element, next is initial node, then final node, then length of the element, then direction cosines. We have two direction cosines, L and M. So here we have only two elements, 1 and 2. Now if you consider this diagram, for element 1, initial node is 1, final node is 2. So I will write the same thing. Initial node is 1, final node is 2, and length of this element is, as we calculated, that is 500. Okay, similarly for element 2, the length is 500 and starting node is 2, that is initial node, and final node is 3. Okay, so initial node is 2, final node is 3, and length is 500. Now here we have to calculate L and M. We know already the formula for L and M. For L, we have x final node minus x initial node divided by length. Similarly, M, y final node minus y initial node divided by length. Okay, so here we have two elements. We have to calculate L and M for element 1 and L and M for element 2. So for element 1, for element 1, L is, as it is final node is 2, x2 minus x1 by L. Similarly, M, y2 minus y1 by L. We'll substitute the values. See here, for the second node, here the distance is 500 minus 900 divided by length is 500. Similarly, y2 is 300 minus 0 divided by length is 500. Okay. after solving this, we'll get minus 0.8, and here we'll get minus plus 0.6. Similarly, for element 2, L is, here the final node is 3 and initial node is 2. So this will be x3 minus x2 divided by length. Here I will write completely, so that here also already we are using L. Okay, y3 minus y2 by length. Here if you consider x3 and x2, that is 0 minus 500 divided by 500, we get minus 1. Similarly, y3, y2, 300 minus 300 divided by 500. Anything minus anything, same thing. 300 minus 300 will be 0, 0 by anything will be 0. You just substitute these values in this table. Okay, minus 0.8, 0.6, minus 1 and 0. Okay, now we'll construct the stiffness, elemental stiffness matrix. Next is elemental stiffness matrix. Already we know how to calculate K. The formula is AE by L, L square ml minus L square minus ml, ml m square minus ml minus m square minus L square minus ml, L square ml minus ml, m square ml, m square. So here we have two elements, so we have to calculate K1 and K2. So for element 1, for element 1, K1 is equal to area is 200 and Young's modulus is 2 into 10 raised to 5 divided by length is 500. Here just substitute L as 0.8 from this table, minus 0.8, that's whole square, because it is L square. After calculation we get 0.64. Similarly, m into L, minus 0.8 into 0.6, so we'll get minus 0.48 minus 0.64, 0.48 minus 0.48, 0.36, 0.48 minus 0.36 minus 0.64, 0.48, 0.64 minus 0.48, 0.48 minus 0.36 minus 0.48, 0.36. Now we have to solve this with the help of calculator. So after solving, we'll get 10 raised to 4 outside. Here we'll get 5.12 minus 3.84 minus 5.12, 3.84 minus 3.84, 2.88, 3.84 minus 2.88 minus 5.12, 3.84, 5.12 minus 3.84, 3.84 minus 2.88 minus 3.84, 2.88. You observe this carefully. Here this element 1 is related to Q1, Q2, Q3, Q4 in order Q1, Q2, Q3, Q4, because node 1 consists of Q1, Q2, node 3 consists of Q3, Q4. So this first column is related to Q1, second one is related to Q2, Q3, and this is Q4, Q3, Q4. Similarly here, this first row is Q1, second is Q3, Q2, Q3, and Q4. Okay, similarly we have to calculate K2. Again in this formula 200 remains same, 200 remains same, 2 into 10 raised to 5 remains same, 500 remains same. Only here the L and ML, M value will be -1 and 0. So after calculation we'll get K2 as 10 raised to 4, 8, 0, -8, 0, 0, 0, 0, 0, -8, 0, 8, 0, 0, 0, 0, 0. Now you observe here, this element 2 is related to node 2 and node 3, that is Q3, Q4, Q5, Q6. So this is related to Q3, this is related to Q4, Q5, Q6, Q3, Q4, Q5, Q6. Okay, next, after this we have to find global stiffness matrix, that is global stiffness matrix, that K is equal to K1 plus K2, as here we have only two elements. For K1 we have two displacement, I mean this is 4x4 matrix, this is 4x4 matrix, and here we have total 6 displacements, Q1, Q2, Q3, Q4, Q5, Q6. So we'll get 6x6 matrix now. Okay, first K is equal to 10 raised to 4 is common. I will construct first 6x6, 1, 2, 3, 4, 5, 6. Here also 1, 2, 3, 4, 5, 6. Okay, I will write this first column is related to Q1, this is Q2, this is Q3, this is Q4, this is Q5, this is Q6. Similarly Q1, Q2, Q3, Q4, Q5, Q6. Now we'll write one by one. First I will start with element 1. Here in this first row, that is Q1 row, first is 5.12, second one is -3.84, 5.12, 3.84. Q2 second row, here we don't have any values. In Q1 row we don't have anything, so 0, 0. Okay, now Q2 row, Q1 column, Q2 column, Q3 column, Q4 column. I will write -3.84, 2.88, 3.84, -2.88. Here with respect to Q2 row we don't have that Q5 and Q6, so I will write 0, 0. Now Q3 row, this is Q3 row, Q1 column, -5.12, 3.84, 5.12, -3.84. Here with respect to Q3, 5 and 6 in this matrix we don't have anything, that is 0, 0. Okay, now Q4, here we have Q4, 3.84, that is with respect to Q1, -2.88, -3.84, 2.88, here it is 0, 0. Here we have only Q1, Q2, Q3, Q4, 4 rows. So Q1, Q2, Q3, Q4, 4 rows completed. Here we have only 4 columns, Q1, Q2, Q3, Q4. So Q5, Q6 remains 0. Now we'll go for second one, element 2. Okay, so for element 2, it starts with Q3. Here I will write with blue pen. Q3 row, here it is starting from Q3 column only. So this is Q3 row, Q3 column, the value is 8. So I will add 8 here. Q3, Q3. Next, this is related to Q4. Same Q3 row, Q4. So it is 0. Again here it is in Q5, -8. Now here last one is 0. Similarly, next Q4, this is Q4 row, this is Q4 row. Here Q4 in Q3 column, 0 plus 0. Q4, this is Q4 row, Q4 column, again it is 0. Here it is also 0, this is also 0, 0, 0. Next, in Q5, Q6, in first element, in Q1 column, Q2 column, we don't have anything, I will write 0, 0. Okay, here Q5 row, Q6 row, this is Q5 row, this is Q6 row. In Q3, we have minus 8, 0, 8, 0, 0, 0, 0, 0. Now we have to add this and we have to write it one more time. So after adding, we get K 10 raised to 4, 5.12 as it is, minus 3.84 as it is, minus 5.12, 3.84, 0, 0. Next, minus 3.84, 2.88, 3.84, minus 2.88, 0, 0. Minus 5.12, 3.84. Here we have to add this 5.12 and 8 will get 13.12. Again here we have to add this 0, again we get same thing, minus 3.84, 0 minus 8 is 8, 0 plus 0 is 0. 3.84 minus 2.88 minus 3.84, 2.88, 0, 0. Next 0, 0, minus 8, 0, 8, 0, 0, 0, 0, 0, 0, 0. Okay, this is global stiffness matrix. Now we have to write global force vector and global, first I will write global displacement vector, that is Q is equal to Q1, Q2, Q3, Q4, Q5, Q6, this is transpose. Similarly, global load vector, global load vector, that is F, F1, F2, F3, F4, F5, F6 transpose. Here according to this figure, we have only one force, that is in downward direction here, that is what, F4. Here F1, F2 0, F3 0, F5, F6 0. Only thing is F4, that is acting downward direction, so we have to write 0, 0, 0, that is minus 12 into 10 raised to 12 kilonewton, 10 raised to 3. Okay, 0, 0, this is transpose. Now you know the equilibrium condition. Equilibrium condition is K, Q is equal to F. Okay, so here K is 6 by 6 matrix, 1, 2, 3, 4, 5, 6. This is Q1, Q2, Q3, Q4, Q5, Q6. Here I will write Q1, Q2, Q3, Q4, Q5, Q6. That is equal to F 0, 0, 0 minus 12 into 10 raised to 3, 0, 0. As from this given figure, you observe this, here it is fixed end, so Q1, Q2 0, here also it is fixed end, so Q5, Q6 also 0. So we have to eliminate respected row and respected column, Q1, Q2 and Q5, Q6. Here this first column, second column, fifth column, sixth column. Only remaining is this one, this one, this one. This is, I will write it from the diagram. After eliminating here, first row, second row, fifth row, sixth row, first column, second column, fifth column, sixth column, only this middle values I will write. 13.12 into 10 raised to 4, I will write in matrix form only, minus 3.84 into 10 raised to 4, 3.84 into 10 raised to 4, 2.88 into 10 raised to 4. Here we have Q3, Q4, and that is equal to 0 minus 12 into 10 raised to 3. Okay, so we have to solve this matrix. First row, first column, first we have to solve like this one into this one, like this, in this direction. I will write 13.12 into 10 raised to 4 into Q3 minus 3.84 into 10 raised to 4, this one, this into Q4, that is equal to 0. Similarly, minus 3.84 into 10 raised to 4 Q3 plus 2.88 into 10 raised to 4 Q4, that is equal to minus 12 into 10 raised to 3. Okay, after solving this, we'll get, with the help of calculator, Q3 as minus 0.2 mm and Q4 as minus 0.683 mm. So same thing we have to write it in there's a vector form, that is Q is equal to, as Q1 is 0, Q2 is 0, Q3 is minus 0.2 and Q4 is minus 0.683 and Q5, Q6, 0, 0. This is transpose. Okay, this completes global nodal displacement vector for the given structure. Now we have to calculate stress. We know the stress formula, sigma, that is E by L minus L minus M L M. Here we have to write Q1, Q2, Q3, Q4. Okay, just we have to substitute this L and M value with respect to element 1 and element 2 from this table. Here already we constructed one table. Okay, so for element 1, L is minus 0.8 and M is 0.6. For element 2, L is minus 1 and M is 0. So after substitution, we will get sigma 1 as minus 99.992 Newton per mm square. Similarly, sigma 2 as minus 80 Newton per mm square. Okay, now the last one, we have to calculate the support reaction. For support reaction, we have the formula R is equal to K Q minus F. Okay, so here first we have to write R1, R2, R3, R4, R5, R6, and K is first outside. I will write 10 raised to 4, 5.12, 3.84 minus 5.12, 3.84, 0, 0, minus 3.84, 2.88, 3.84 minus 2.88, 0, 0, minus 5.12, 3.84, 13.12 minus 3.84 minus 8, 0, 3.84 minus 2.88 minus 3.84, 2.88, 0, 0, 0, 0, minus 8, 0, 8, 0, 0, 0, 0, 0, 0, 0. Here we have to write the displacement values. first is 0, q1 0, q2 0, then it is minus 0.2, and q4 0.683 as we calculated 0 0. And here minus we have to write the forces. All the forces are 0 except the F4. 0 0 0 minus 12 into 10 raised to 3, 0 and 0. Okay, I will show you one how to calculate. R1 is equal to first 5.12 into 10 raised to 4, this first value 0, then minus 3.84 into 10 raised to 4, this one, and the second element 0, then minus 5.12 into 10 raised to 4, this is third one, here we have to multiply with minus 0.2. Okay, then plus 3.84 into 10 raised to 4 into the fourth one is minus 0.683. As here it is 0, 0 into anything 0, 0 into anything 0. Then after getting this value, we have to subtract from this force. Here we have 0. Okay, like that we'll get R1 as minus 1598.72 Newton. Similarly, this second row with this column, third row with this column, fourth row with this column, fifth row with this column, sixth row with this column. First you have to solve this and you have to subtract from this force vector. So we'll get R as minus 159872 Newton minus 11990.40 Newton 0 0 1600 Newton 0. Okay, this is the reaction at the support. This completes the problem. Thank you.